in our right. So in our last class, in the last class, we actually looked at how we can solve problems regarding the laws of motion, right? Sorry, not, what do you call it? The Sauer's equation. We solved everything regarding that, right? And we completed it. I gave us different templates or different ways on how we can apply the Sauer's equation and how best that we can navigate them. And I hope that we understood everything that we did that very day. And as well, we did projectile. Yeah, I think it was projectile in the last class. So I was making reference to the second to the last class. So we looked at projectiles. So let me quickly review that very material on projectile as fast as we can. So we looked at projectiles, and under your projectiles, I had to make reference to a few things, right? We solved questions that very day. I started by introducing a few things, right? I had to make a difference or a disparity between vertical motion and horizontal motion. And then I went straight to your horizontal motion. I spoke about vertical motion. Then I spoke about your projectiles, right? And I solved some questions on projectile motion, right? We solved a good number of questions: time of flight, total time of flight, maximum height, range, and the rest of that. And I solved a lot of examples. And I also told us to go check out past questions so you can solve more problems on that, right? These are the ones we solved in the class. And today we'll be going straight up to another interesting aspect, right? Which is the laws of motion, right? We know there are three laws of motion. We'll be looking at those three laws of motion. We'll be looking at momentum. We'll be looking at impulse, right? We also learn how to draw your free body diagram today. So all of these things are key things that we'll be looking at today for this very topic. Now, it is important to know these key things I'll be highlighting now. It's really, really important that even if we don't cover them, you should actually take that to heart, right? So, you should know that they were going to ask you basically the meaning and applications of Newton's law. So the first thing you need to know is the meaning and the applications. So take that to heart and ensure that you grab that very concept. So number one is the meaning and applications of Newton's law. Right. So the next one, you should be able to identify the forces acting on the body. Right. You should be able to identify. Right. So identifying. So these are the objective of this very lesson. So anywhere we stop, go do well to get your textbook, watch videos, right, and that would help. So identify forces on bodies. There are example, right? You should have the weight, be able to draw the free body diagram. You should have your weight. You should have the normal reaction. Normal reaction. You should have friction. You should know how to represent if there are things on tension. You should as well know how to go about that. Now, you should have ideas regarding your resultant force, right? Which I've taught us how to get a resultant when I did vectors. So you have to pay attention to your resultant force and your acceleration. Resultant force, which can also be called your net force, and acceleration. How to apply those formulas is very, very key. Now, the fourth thing you should pay attention to is your impulse and momentum calculations, right? And after that, there should be your first time graph, right? How to estimate your impulse from the first time graph, right? So we have the first time graph. right? After which there should be the conservation of momentum, where you start learning about elastic and inelastic, right? Collisions. So that is where we know about the conservation of momentum. Then you should know about your inertia and how it affects acceleration. All right, so that's for that. So do well to actually get used to all of these things, and that will really help you, right? Overall. All right, so let's kickstart with force, right? So what is force? Force is simply the push or pull, right, on a body that can actually change the speed of the body. It can change the direction of motion. It can as well change the shape of the body, right? So when you make reference to force, which is what almost everything in physics revolves around, there are key things that comes to the mind when we talk about force, basically, right? What are those things that comes to the mind? It tells us that we have a push or a pull or a pull on a body that changes, that's going to change. The first thing is going to change, right? Is going to change the speed of the body, right? It's going to change the direction of the body. This one I'm drawing love this morning. What is happening? I think it's a sign that something wonderful is going to happen to me this week. Maybe I'm going to locate the bone of my bone. This is direction of motion. Direction of motion. And then the third one, it changes the shape of the body. All right, all of us, we're not new to all of these things, and you know the unit of force, right? And it's important to as well know that there are two kinds of force, right? Sometimes you're going to see questions on that. We have our contact force, and we have the non-contact force. Now, what's the difference between the two? When someone slaps you, that's a contact force because the force being applied is in contact, in direct contact with the body receiving the force. That's your contact force, right? So when I slap you, right, it's contact force because there is a direct interaction between the object and the force. But for non-contact force, there is no interaction directly. There's no direct contact. So this one's do with a direct contact. There's no direct contact. Now, back then as children, I know you guys might not actually play that kind of things, but then, yeah, we did that. We grew up in the part of the world where we did a lot of that, basically. So what am I talking about? You have a paper. Back then, you get paper, and then you pour sand on the paper. I'm trying to explain non-contact force. You pour sand on paper, and you have this magnet. You place magnet under the paper. As you're moving that magnet, back then we even had to draw a pathway for it. We have a pathway, right? We have pathway. We even draw a very fine road. Even sometimes we put a roundabout about that. So what we do is that we place the sand here, and then there's a magnet between. So as I'm moving the magnet under the paper, this sand is moving. You can direct it any way you want to direct it. If you know some of those things, can you give me a thumbs up? I think the only person that might know if he's still on the call is Mr. Hillary. He might know this if he's still on the call. Yeah, Justice, he must be an old man. Ah, even Mesa, you know this. Interesting. Interesting. I know people like Titilola might not know this, all those Indomie generation, they might not really know this, right? So as you're moving that magnet, but if you know it, you're a high star, right? And you should be married by now. If you know those things I'm talking about, if you know, you should be married by now. Mesa and Justice, I know you guys should be married by now. All right, so it's really beautiful and wonderful, right? When you keep moving those things beneath the paper and the sand is moving, right? Susan, do you know it? Give me a thumbs up if you know what I'm talking about. You will not know. You will not know. Yeah, I know. Some of you that you barely go outside, they lock you inside the house and then feed you spaghetti and indomie. How will you know it? So now, but it's a very interesting game. Like, it's more like as you're moving the magnet under the paper, the sand is moving. It's an example of non-contact force. Why is it a non-contact force? Because the magnet is not in contact with the what do you call it? With the sand, but the sand is moving, right? It is feeling the effect of the magnetic field, right? Now, the next one again that we normally do, we'll call it magic. Is back then that you will tell somebody to hold a stone. This person will hold the stone. This person will hold the stone for a long time. Then you are passing the stone like over. You pass it 1, 2. You are passing the stone. You pass it. You collect it under. You pass it. You collect it under. Yeah, Paul. I know you know it. This guy you played. For car. Are you sure you are not among those that will normally set pen for somebody when they want to sit down? So now you pass. So you pass the stone. As you're passing the stone, now you tell the person to pull their hand. It's as though it's there's this gumming force, like as if it's difficult for you to pull. There's this force of like you're feeling that force, that heaviness. Can you remember? Right? So all of those things fall under the non-contact force. I don't know the example I will use again, but these are the illustrations coming to my head. But it's unfortunate that only a few persons in the class know what I'm talking about, right? So when you are feeling that force, that's what we regard as your non-contact force, right? So if I'm to give examples of contact force, we could have things like a pull, right? You can have normal reactions, So for your contact force, okay, Titilola, your hands are up, please. The stage is yours.
Sir, to be honest, I don't really understand the contact force.
Okay. Now, what will happen for you to understand? Are you at home?
Yes, sir.
Okay, who is around? Do you have any of your siblings around?
Yes, sir.
Okay, can you meet? Is it maybe the one that is let's say not your younger sister, your elder brother or elder sister? Is anyone around? Any of them around?
Yes, sir.
Okay, just meet one of them. Tell them to slap you. You understand contact force. Once they give you a slap, that is contact force. Is that okay?
No, it's not.
It's not okay. Once they slap you, that is contact force.
I mean, I can try doing it. Let me be the one that is applying the force.
Okay, now once they slap you, now your face is in contact with that slap. Do you get the point now? That is contact force. Just give it a try, you understand better. And meet the one that maybe you annoyed yesterday. Your sibling you are going to meet is the one you annoyed yesterday, or maybe earlier this morning. So you understand this contact force better. Do you get the point,
Okay,
Titilola?
sir. Yes, sir.
So it has to do with the object being in contact with. Remember, we said that a force is a pull or a push. So when you are in contact, direct contact with that pull or push. Example: if someone slaps you and your face is not there, will the slap get to you?
No,
No,
sir.
unless you are under anointing. Maybe the pastor does his hand, yeah, then you're on the ground. You get, so that one is non-contact force. So the moment that they are praying in church and then someone does his hand like this, receive it, and someone is falling, that is non-contact force, because you are not, the person is not touching you, but you are falling. Right? I'm not talking about those that pull leg for people, sure. I'm talking about people that just do hands and then things begin to happen, right? So that one is a non-contact force, right? And also when the body is in contact with the pull or the push, that is what we regard as contact force. Does that make sense now? Titi Lola, does that make sense? Or have you received the slap? All right. Now, another example for non-contact force. Check. When you have something like a nail and you have a magnet here, what do you notice? What will happen? Even when the nail is not close to the magnet, what happens? As you're holding that nail on your hand, it's as though the nail is trying to go closer to the magnet. Good. The same thing that happens. Should I say this, brethren? The same thing that happens when okay. Now, the same thing that happens in terms of your non-contact force. When you have a fair dam cell here, and then you have Paul seated this side, and there is another, then Justice is seated here. When both of them are together, nothing is happening. But there's something that is pulling Paul to the fair dam cell, even when they are not in contact. That is non-contact force. Paul, Sister Lola, I hope it makes sense now. All right. Good. Paul, I know you're innocent. I know you're innocent. I'm just giving an example anyway. But it happens. If it doesn't happen to you, then you need to go to the church for prayers. It should happen to any normal human being. It's wired inside of us. But then I know you're a good guy. All right. So contact force now. Examples, you have your normal reaction. You have normal reaction. I know we are all good boys, and we're raising good boys in this very place, right? We just have to apply what we call self-control. You have to control yourself. As you are saying this one fine, you tell yourself it's not your time. So we have tension. Man and brethren, hope I'm the young men in the house. Hope I'm on point. Yeah. Good. I think it happens to the ladies as well. Some of them, don't mind them. Titilola, you lie. You lie. Hey, you lie. If it doesn't happen, then there's something I tell my teenagers back then in church, right? I tell them, it's important I say this as well as you're growing up as young people. I told them, if you are in SS2 and there's nobody in your class or people around in your area disturbing you, please go to your mom, tell her to pray for you. So when I said this, they don't understand what I mean, but it's normal, that shows you are a human being, so they should. And if they are not coming, then there's a problem somewhere. So it's normal at that age, but the only thing you need to do is to tell yourself that you know what you want to achieve, right? And you want to make your parents proud. You want to as well create an impact, right? So it's something that keeps you going, that keeps you focused. But the distractions are going to be there as long as you are on planet Earth, right? And I believe I have good persons on the call that want to do a lot, that want to achieve a lot, that want to put a smile in the face of their parents, that wants to make impact in other young people. I believe I have them on the call, right? So all the best. I'm rooting for all of you. For our ladies in the house, I'm rooting for all of you, right? Thank you. So now we'll have the non-contact force. All right. We'll have the non-contact force. So it's not something we should run away from talking. We should always say it. So we'll have the magnetic force, right? That's the magnetic force. Good. There's another one I remembered now. We'll have electrostatic. I think I'm taking so much time on this contact force. We'll have electrostatic. For electrostatic, there's something we normally do. I think I played a lot back then. You take your pen, right? Take your biro, and then you kind of scrape it on your hair for some time. Then you get a small piece of paper. As you are bringing that pen closer to the hair, what happens? It traps it, right? The pen doesn't need to come in contact with the hair. It just traps it. Titula, did you do that? Why I know you didn't. You were such a good student back in school. Titula, did
Yes,
you do
but
that?
another one that I know.
You know this one, right?
Yes, but there is one after ironing clothes. And you bring it close to
Yes.
your body, your hair will rise.
Your clothes will rise.
Your hair, the hairs on your body will rise.
Yeah. This guy makes sense. So you are just coming in contact. You're not bringing it close, right? So that is also non-contact force, right? Quite interesting. Well done, Justice. That means you. That's why I like physics. Physics is quite interesting. Very, very interesting. Now, that's your non-contact force. You can highlight a lot of them. Have electrostatic force, magnetic force, right? All of those things are under your non-contact force. That once they come around, you begin to feel them, right? Yeah, Titilola, you're such a good girl, actually. You're such a good girl, right? But you missed a lot. You missed a lot. All of those things are stories you can tell, right? You can tell. Hmm. Sorry, she missed a lot, actually. But you can start doing them now. It's not bad. It's not bad. It's not bad. Just that you'll be raising alarm in your area. Maybe you force your parents to start taking you to the hospital. When you start doing that now. All right. So we have the resultant and net force. So that's why at every stage of life, ensure that you anything that's the good ones you should do at that age is very important that you do so, right? So you have a story to tell. But still, it's entirely fine. When I grow up, I wish to be like you, so that all of those bad things that they did, I won't have experienced it. Now, what's your resultant force? It is more like a single force that has the same effect all combined together. Is that also? I said that the last time. So when you have plenty of forces acting, let's say we have a force acting this way. I think I shouldn't waste time on this. We have another force acting this way, right? So when you tend to get the resultant force, that's let's say we have F1 here, we have F2 here, then you have a single force that represents everything, right? So let's call that your F. Let's say everything. We have a resultant force here. Let's call it F, right? So that's how to get the resultant force. Now, if the resultant force or the net force, right, anyone they call it, is entirely fine. But I think for motion, you always hear net force, right? So if the net force is equal to zero, brethren, if net force equals zero, that means the resultant is equal to zero. When I say net force, I'm talking about resultant, right? Just using the term you'll be seeing more often in motion. If the net force is equal to zero, it means that what? That the velocity is constant or the body is at rest, no acceleration. So net force equals zero simply means no acceleration. And no acceleration implies what? No acceleration implies, it implies what? Constant velocity. Remember the constant velocity on that our graph is that straight line, that horizontal straight line like this. We say that that's constant velocity, right? On our velocity time graph. Constant velocity or the body is at rest. Right? So when the net force is equal to zero, automatically that's what it implies, right? The body is not moving or there's a constant velocity, right? All right. So that's the basics of your resultant and net force. Always remember they will give you those directions, acceleration. I'm going to show you the free body diagram, and you're asked to find the net force, right? Ability to know some of those things is going to give you a powerful edge right away. All right, now. Uh So let's proceed. Meanwhile, there's a form on the group. I think it's only four persons, which is Titilola. I can't remember their names. I don't know. I think Mesa have filled it. Then I think Confidence have done that. But a good number of you have not filled that form. After this class, ensure you do that. Else, you are looking for my trouble. And I will change it for you. All right. So the Newton's first law. You're asking me, fill form, you're asking me the form is for what? Huh? Susan, you're asking me the form is for what? Interesting. Mm. Fill the form first. The form is there, right, waiting for you. When you open the form, you know what the form is for. All right, well done, Paul. Paul, I think you filled it. I can't remember. Yeah, you have. So we have the Newton's first law. I think Paul, Titilola, Mesoma, and Obasi Confidence. These are people that have filled it. The other ones are forming strong head, but I will deal with them personally. So now the Newton's first law, when you talk about Newton's first law, the first thing that comes to your mind is inertia, right? I hope I'm pronouncing it well. Inertia, Natasha. Oh, okay. Dauda Baraka. Hope I pronounce that name very well. I'm going to send the form to the probation group. Is that okay? Can you give me a thumbs up? All right, beautiful. Hope I pronounce the name very well. Okay, so for the law of inertia, right? That inertia is simply the tendency of a body to remain at rest or to continue moving with constant velocity in a straight line. You know, when I mean constant velocity, what do I mean? Yeah, you pronounce very well. Yeah, I'm too good, bro. I'm too good, bro. I think you should give me a thumbs up, man. So now, the inertia simply means it remains at rest and it continues moving with a constant velocity. Now, when I say constant velocity, something should come to your head. Constant velocity means that body is moving in the same direction and also the what? The same speed. These are two things that should come to your head when you hear constant velocity. So the law of inertia, you remain at rest, and the tendency of a body to keep moving in a particular direction, right? Maintaining a particular motion. And that is how this inertia is what is affecting us generally in life. We just want to stay there. We want to stay at it. We want to keep doing that thing that we're doing. We want to stay in our comfort zone. Nobody wants to push up. So anything that tries to pull you away from your comfort zone, you still want to go back to it again, right? That resistance is normal, it's natural, right? So that's why physics has dedicated that law of inertia because it's something very, very key. Even in real life, you know, aside normal motion and the rest of them, has to do with our mindset as well. The normal human body does not need stress, and that's why some of us will go to church, you know, and during preaching, you start sleeping. But you notice something that once they finish preaching, the sleep will leave you entirely. Your eyes will be open for so many hours. Right? So that is also inertia because the body just wants to be comfortable. It doesn't want anything that will stretch the heart and the mind. Right? So, and that comes into play in different areas. So for your jam, let's bring it home. What does jam want you to know about inertia? Jam will be like, you know, when you are in a vehicle, let's bring it home. I'm saying all of so you can always remember it. At least I give an example of some of you that sleep in church. There was a young man back then that he just woke up and shouted amen. The church was very calm, right? Everyone was very calm. So maybe when he slept off was when they were shouting amen, you know. So basically he now woke up and shouted his own amen, and everybody looked back. You know how it can be, that kind of feeling, you know. So the young man felt so bad. So sleep can be very terrible. All right, so you have your vehicle right here. You have this vehicle right here as well. Now, if you're inside this vehicle, this my what do you call it? My Benz, right? And as the vehicle is moving, let's say you are standing, right? You are standing, or even you are sitting on. Let's use stand in the vehicle, right? This is the first person should be Titilola and the rest of them standing. Now, as the vehicle is moving, right? You are moving as well. Yeah, that's a new vehicle. It looks like footwear. Yeah. So as the vehicle is moving, your body is moving as well. Now, but when let's say that Paul is a driver and is a very rough driver, so all of a sudden he matches the brake like with force. What happened when he matches the brake? You notice that you're going to jerk forward. Is that not so? You're going to do what? Jerk forward. Like your body will move forward, right? Why are you moving forward? That's why sometimes it's advisable to wear seat belts so that when that happens, your head will not hit the glass. But I don't know how they should try and put seat belts in keke. because I had an encounter. Someone was sitting in someone was sitting. I know what I'm talking about. Someone was sitting in front of Keke, right? And something happened. The guy matched the brake by like suddenly. The woman said nearly hit on that glass. The woman in front of that place. So if you are sitting there, very careful sometimes, so that your head will not open up the glass. So, and I was so surprised. So why are you jerking forward? Because the body wants to continue moving in that very direction, right? Even when there's an apply for, you still want to keep going there. So that inertia is the tendency of a body to either remain at rest or to keep continuing that very motion that it is going. Another example, let's say that all of us are seated in this vehicle. All of us are seated in this vehicle, right? We are relaxing, talking, right? And all of a sudden, the car starts moving. What happened? You're going to jerk backward. Is that not so? You're going to move like responding to that forward movement. You're going to jerk backwards. So why are you jerking backwards? You are jerking back because you want to continue at rest, right? So these are the examples that they are going to give in terms of a vehicle suddenly stops, you jerk forward, you jerk backwards. All of them revolves around the law of inertia. Is that okay? And now, the heavier you are, the more the vehicle cannot contain us. That's why you should save money so you can buy more, right? You buy baba. There's something we call baba here in the east. That when you enter, possibly before you come down, someone will be like, brother, there's an opening in your clothes, maybe towards the bucket side. You enter with a good clothes and then you leave with a torn clothes. It happens here in the east. So now, take note of that inertia, right, and how it works. So I've given examples. I'm not writing those examples here, but that's why you are in class to always remember when there's a question around inertia. So now for inertia, is simply the tendency of a body, and that gave birth to the Newton's first law. Tendency of a body. Tendency of a body. Hope we're learning something this morning. Tendency of a body to remain at rest. Yeah, beautiful. To remain at rest or continue moving. And I said what I mean by constant velocity. I said same direction, same. In simple time, you just want to remain on a straight line with constant velocity. You want to maintain that motion, right, in a straight line. I've given you examples. Please always remember those examples I gave you. And it's important to know that inertia depends on mass, right? Inertia depends on mass. It's very, very key. Take notes. Inertia depends on mass. It's something very important to note. So the bigger the mass, the more the inertia, right? The more the tendency of that body to remain at rest or to keep moving in that direction that it is moving, right? So that's why it's expected that you don't carry so much weight, right? So much people to be distracting you, so much friends, right? The more the friends, the more the distractions. So more mass equals more inertia. Yeah, that's the fact actually. All right. So I've given examples about your Newton's about inertia. So what is now your Newton's first law, right? Now the Newton's first law, we can also call it the law of inertia, right? So Newton's first law, which I've already said, right, which is the law of inertia. For me, teaching this is the part I detest so much. That part of explaining defining things, explaining. I want to just solve. I prefer solving questions, but it's unfortunate you have to introduce before you solve. So now, it says that the body remains at rest. Body remains at rest. Is Ferrami on the call? Or moves? Ferrami, are you on the call? So sorry, there's something I would have sent, but I just forgot. Maybe that's why you're not in the class. Constant velocity in a straight line. So let's acted upon by a resultant force. All right. Now, remember I told you that constant velocity, same speed, same constant speed, constant direction. So if a body moves to constant velocity, the net force is equal to 0. So that's all I want you to know for that. Now, second law is where we're going to get our hands dirty, right? And I would like that so much. It's not difficult actually, so it's not something to be worried about. All right, Newton's second law of motion. So that law says that the change of momentum is proportional to the applied force, right? And it occurs in the direction of the what? Of the force. So let's do a little bit of proving, right? So that we have a context to the Newton's law of motion. If you're still with me, can you give me a thumbs up, please? All right, I have Susan, I have Ugu, Godlia, I have Tinosu, I have... Yeah, who is Nikki Gold? You know the answer name for this class. Nikki Gold. Yeah, no be small thing. How can you combine two elements as your name, nickel and gold? That person must be very good at chemistry. Maybe when she joins again, I will suggest another name for her. Nickel Gold Silver. Ah, it will be very beautiful. Just put silver at the back. So the rate of change of momentum of a body is proportional to the applied force. Proportional to the applied force and occurs in the direction of that force. All right. So now, what does it say? Now, it simply says that your force is directly proportional. That is equal to, yeah, Nikki Gold, welcome back. So Nikki Gold, I said that your name is quite good, that you should know, you know a lot of chemistry. That is why I combine nickel and gold. And I was suggesting you add silver to the back of the name, nickel gold silver. That would be very, very good. Right. So now we have that your force is proportional to change in momentum, right? All over. You have your time, right? So this is the Newton's second law. So where you should know that your F is the force, P is change in momentum, then over time. Now it's important to know that momentum is mass times velocity. Everybody should know this at this point, right? Now remember that change in P is it not really P like small p, but because of the Y, right? You know, boys are not getting any younger. So this is P here. This is P here. So change in P is equal to what? Change in momentum, right? So this is change in momentum. You know what F is already? F is the force. So change in momentum. Now, momentum itself is what we call agrima in Igbo. So momentum, I don't know what you call it in Yoruba or in Hausa, but then we'll call it agrima. Like when I mean agrima, I mean you know, when you are playing ball, you want to put body for somebody, like you just crack the person a little bit, you know. So momentum is equal to your mass times velocity. Is that okay? So now, and this can be written as MV. So that change in P will now be equal to what? MV minus MU. Are we together now? So that when we collect like terms, we can have that change in momentum is equal to MV minus U. Remember that change in V is your initial velocity, U is your final, U is initial velocity, and V is your final velocity. Are we all on the same page? Right, good. So let's proceed. Thank you, Mr. Paul. Thank you. All right. That said, I think we can continue. Benita, welcome. How are you doing? Hope you're good. Just notice you're on the call. You are doing a lot. Combining school with writing jam is not easy. Well done. I'm rooting for you as always. All right, so let's go back to give me a thumbs up if you're still with me, Benita. So you have force change in T all over time. I said Benita and good is giving me thumbs up. Hold your good. Now we have that F. Good. We have that F is equal to, so let's plug in the value of my change in P. That is M open bracket V minus U. We'll close it divided by your what? Your T. Right? So this is your Newton's first law. But I want you to understand something here. Pay attention to this part of the variable. You are going to see something very interesting. Right? Pay attention to this side of the equation. Pay attention to this side of the equation. You are going to notice that there is something, right? So now this is your Newton's first law, second law, that has to do with your momentum and your force, right here. So what can we observe right here? We could observe something quite interesting. And you can see that acceleration A is equal to change in velocity over time. Therefore, we are going to plug in that very value into our equation. And when we plug in that very value, titular on point, when we plug in that very value into the equation, we are going to have that, let me call this equation number 1. Okay, let's call this equation 1 so that will be orderly. Let's call this equation 1. Let's call this equation 2. Sometimes I wish I can cover all the topics in your syllabus, but then unless we're going to be doing marathon, but I can't do that. I'm busy as well, but I wish it's something I could do, sincerely speaking, but then I'm limited. So what I'm going to do from next week, keep your eyes on your dashboard. For each week, we should have a goal. So I'm going to upload all the videos I want you to watch, video lessons on those ones I cannot cover or we cannot cover in physics. So you watch them yourself, right? It's going to help you. So now plug in, let's substitute equation 4 into equation 3. Keep your eyes on that dashboard and watch those videos. Sub equation, for people that want to do that, I'm going to do it for you. Sub equation 4 into 3. Maybe if I, oh my God, I'm still drawing. What is happening? What is happening? This is a signal. F equal to MA. All right, so let's have this to be my equation number 5. All right, so you've seen how it's reduced to what? F equal to MA. So these are the two equations that can actually come out from your Newton's second law, right? So general form of the Newton's first law, the general form is your equation number 3, right? Which now reduces to what? Equation number 5 for a special case when M is constant, right? So this is a special case, right? Okay, go ahead, Mr. Paul. Olu, wow, Oju.
Sir, I have a question.
Go ahead, my bro.
So the law says the force is directly proportional to rate of change of momentum.
Momentum,
Which
yes.
means there is a constant. Since we have the proportionality there.
Yeah, there is a constant. Yeah,
Yes,
makes sense. You're asking a very powerful question right there.
But
Since you have
this equation now makes us understand that the constant is 1.
The constant is what?
The value of the constant is 1 because we cannot see
beautiful. Any proportionality constants.
My question is, how do they determine the value of all these constants? Like this one now we have 1. For gravitational, we have 6.6 exponential minus 11. For
Mm-hmm.
all those, how did they come about all those constant values like that? That was my question.
Okay. Now, if I got your questions completely, you said from your knowledge of mathematics, right? We know that when people say that F, for example, let's say that A is directly proportional to B, we should have that A is equal to what? K B. Is that not so? Right. Good. Now, if we go straight to knowing why we have that F, right, is proportional to change in momentum over time. Actually, there is time actually. Change momentum with time, right? Now, there should be a proportionality constant. Are we together now? Now, you should have F equal to K change in P over change in T. Are we together? Good. Now, but the unit of force, I hope others might not. Do you guys understand the question he asked? Right, but let me answer him first because the person that needs it. Yeah, good. Now, like you said, K is equal to 1. You are very correct on that. So, but why is K is equal to 1? It is because the unit of Newton, the unit of force, which is Newton, is actually based on this second law. The unit of force, which is Newton, is based on this second law. Confidence. Wait, let me answer this one before you come through now. Are we together now? Now, we look at it is that the force that produces an acceleration of what? Of 1 meter per second squared in a mass of 1 kg. Now, remember that when you are getting your proportionality constant, are we together? When you're getting your proportionality constant, remember I can also write this thing like this. When I say that F is directly proportional to change in momentum all over change in time, right? That I'm also saying that F is equal to K M A. Do you agree? If you agree, give me a thumbs up. Good. Now, Paul, look at what I want you to do. Focus on this reduction of the equation now. That it moves from here to here. That's step 1. Now, the next thing is that we want to get the value of K, right? So K will be equal to what? F all over MA. Is that not so? That's the value of your K. Now, we are going to assume that our mass is 1. Are we okay now? We're going to assume that the mass of the body is 1. The acceleration is 1. So when the mass is 1, acceleration is 1, it means that my force is equal to 1. Are we together now? So you are using a unit of 1 to get the value of K. Now, because of that, we make use of what? A constant of 1. We say that our K is 1, which gives birth to your 1 Newton. 1 Newton is equal to 1 kg meter per second squared. Now, let me recap again for those that are confused. I start from beginning again. Okay, let's go again. Look at what I said. F is direct proportional to change in P all over time. Let's put T here, right? Now we have that F is direct proportional. After we converted, we saw that this is what? MA, right? Then we have that F is equal to KMA. Our assumption is that K is equal 1, proportionality constant, and that M is equal to 1 meter per second. Sorry, M is equal to 1 kg. And then we say that A is equal to 1 meter per second squared. So that F will now be equal to 1 times 1 kg times 1 meter per second. So that your force will now be equal to what? 1 kg meter per second squared. And that is where we got the unit of force. Unit of force, Newton, simply means kg meter per second squared. So 1 Newton is equal to 1 kg meter per second because we assume that the proportionality constant is equal to 1. Right? That is where the assumption comes that gave us the unit of Newton. Paul, I don't know if I answered your question.
Yes. Now we have gotten
Oh,
the
yes.
units. I mean,
Oh,
now
okay.
like You see, many constants in formulas usually have
Yes.
some have high values,
Okay.
some have low values. This one
Low
has
values.
one.
Yes.
So now
Yes.
my question is, how do they determine the value of those constants?
Of the constants. Now,
Yes,
I get your question now. Why? How did they determine the values of the constants? Now,
yes,
why we do this? Why we do this is that we consider our SI units. Now, if you can remember in your chemistry, let me take you down the road. When you did something on what do you call it? Electrolysis. When you determine the unit of Z, can someone remember this formula? That's Z, M proportional to Z to Q. Then you have that M is equal to K, KQ, ZQ rather. When you did the laws of indices, sorry, laws of electrolysis, I mean to say, first law of electrolysis, second law of electrolysis. Yes. So all those constants is, as we are choosing those constants, we are doing that based on our units. Is the SI unit that guides us. I might not give a comprehensive answer, but the basic thing that happens there is that we look at our units, right? We look at our units. So you see, anything that has to do with science is there. We are looking for how to solve our problems, right? Electrochemical equivalence. God bless you, Chinoso. Good. That's what I'm looking for. Electrochemical equivalence Z. That's the same principle that applied in electrochemical equivalence, where we have to make use of one. The time it takes one of these things to discharge. Do you get the point now? So we make reference to things that will make our work easier for us. I'm also trying to remember something again that has to do with a place where we assume some things, right? And so that it can make things easier for us. There are some assumptions you make. Example, you are solving a particular question, and we assume that air resistance is negligible. Why in the actual sense is not negligible? Are we together now? So, in summary, to answer your question, is that in sciences, there are assumptions. That's why sometimes I'll crack a joke. I'll be like, it is when solving questions that you make assumptions. In real life, there's no assumption. But when it comes to theoretical work like this, we assume a lot of things, right? Because you have to make assumptions to solve your problems. Else, you're going to sleep there. As long as sciences and engineering is concerned, yes. I'm also trying to remember another thing that we did. There was a question we were solving the other time that we had to assume something. Good. Now, you give something like this, they'll give you equation to, they say that x equal to x minus 1, right? They will not be like, where x is not equal to 0. It's an assumption because they know, okay, let's put the other way around. Something like, let me use, okay, they have x minus 1. Good. They'll not be like, where x is not equal to 1. Because you know that if x is equal to 1, you're going to have x 1 minus 1, x over 0. That will blow up undefined. So we have to assume so we don't have that kind of situation. Paul, does it make sense now? Mr. Paul? Good. So I'm talking I'm talking based as an engineer now. I study chemical engineering now. As much I'm doing all this is for you guys now. So from the point of view as an engineer, we make assumptions so we can get our answers, right? As long as theories are concerned. But you are going to make sure that the assumption you're making is reasonable, right? So you assume some things to get your answer. I know some persons are not so. You are thinking as a scientist, and I like that. You want to do engineering, right? You are thinking so deep, and I love that. I know some of the ladies in the car are confused at this point. So let's come back to our question. So sorry about that, guys. It's important to clear his doubts, right? So Paul, it happens, okay? You make assumptions so that you could get to where you are getting to. Yeah, I asked that question as well. Mhm. I asked that question as well. There are some points in engineering we have to assume the boiling point is 80. I'll be like, why are you assuming it is 80 degrees? How do you know it is 80 degrees? You know, they'll be like, that's how we can actually navigate to get what we need. All right. So F equal to MA, which is a special case, right? So yeah, assumptions are allowed basically. So based on assumption, K is equal to 1. But some of them can be tested experimentally. Some of those constants can be tested experimentally, right? So it's important you take note of that as well. Any question again, guys? So second law, Taco. Titi Lola, are you here? Abi, that question not even concern you. Maybe they kill themselves, they find assumption, Abi. All right. So let's move. Okay, that's not that's not. Let's go back to the third law. Are we together now? Yeah, let's go to the third law. Yeah, physics is a very interesting subject, and that makes a lot of sense, and I'm enjoying it. All right. So for your third law, it says that action and reaction are equal and opposite. Action and reaction are equal and opposite. Is that okay? That's why when you slap somebody, your hand will also feel the pain. Is that not so? Or when you hit the desk, right? When you hit your hand against the desk, your hand will feel the pain as well, and the desk is going to make noise as well. That is because there's something we call the Newton's third law that says that action and reaction, they are equal and opposite. That gave birth to Newton's third law. Now, this is where I'm going to give some examples that plays out in your exam so much, right? So for every reaction, for every action, there is an equal and opposite reaction. There is an equal and opposite reaction. So what does that entail, right? They are equal in magnitude. Do you get the point now? They are going to be equal in magnitude, but opposite in direction, right? So for every action, it acts on a body. So this action is more like a force. The reaction is also a force, right? But they act in different direction, but they're going to have the same magnitude, right? So action and reaction, they are equal and opposite. Let me use examples, right? Now, a key example is, like I said, when you hit your hand on the desk, that force you are applying on that desk is the action. So you hit your hand on the desk, you have an action. The desk again gives its own force. That's the reaction. Another example is when you are seated on a chair, right? When you sit on that chair, are we together now? When you sit, your weight on that chair is an action. The chair again will respond, right? It will exert, you're exerting force on the chair. The chair is going to exert its own force on you. That is what your reaction. Now, but something will happen when you get somebody that has so much matter, right? I'm not making reference to anybody, but when you get someone that has so much matter, on this same chair, you have someone else that doesn't have so much matter. The person sits in this chair, nothing happens to the chair. Someone else comes to this place to sit down, and the chair is gone. The legs, they spin to oblivion. The legs, something happens to the leg of the chair. Why does that happen? It's because the action of the person is more than the reaction. So the reaction the chair is giving back is less than the action, and the chair will break. That's what I'm trying to say. Like, I mean, someone that is occupying till Jesus returns, right? When they sit on the chair, when it breaks, it means that the reaction is no longer equal to the action. But when someone that is slim sits on that chair, just like me, nothing will happen to the chair. So action and reaction are equal and opposite. Another example that you need to know in terms of jump is when you start hearing that the recoil of a gun, right? So the gun and the bullet recoil. So when you fire a gun from the sorry, English. When you fire a bullet from the gun, right? What happens is that there is an explosive force that pushes the bullet out of the gun. And as the bullet is going out, it has a backward force on the gun. That's why not everybody can shoot. You've watched movies that they get someone gun to shoot after they go and throw that person out, like after the bullet left the gun, right? You've seen that kind of thing. So when you are shooting, there's this kind of balance they give to it so that it doesn't pull you out. That's the recoil of a gun. That's what we call it. So as the bullet is going forward, it has an opposite force, right? That pushes the gun backwards. And in response, it can throw out or throw off the person that is handling the gun. Right. I know some of you don't know, you can even kill cockroach, talk more of handling gun. So, but then just understand that in movies that kind of thing happens, right? And we'll call it the recoil of a gun. The next one has to do with your rockets, right? Has to do with your rockets. Now, if you are too good with movies, or you've seen anything regarding rockets, you're going to notice that as the rocket is moving, there is this gas that is expelled from the bottom of the rocket. Why are you laughing at my kite or my rocket? I will sack you from the call. So now, as that gas is leaving out from the bottom of the rocket is propelling forward, and that forward motion is what we call the thrust. The class is too cold. Are you following me at all? Good. Yeah, Nikki, good. Nikki, good. Okay. Ezetchinonso, Benita, Fave. Okay, Benita. Yeah, good. Who again? All right. I hope Titilola is still here. Yeah, Lillian. Yeah, Ugu God. That your name is Titilola. What's the problem? You confused? Okay. Ugu Godliner. I don't know how to pronounce that your name actually, but we don't understand your rocket. But do you understand the concept? Leave my diagram, right? It's just for you to understand what I'm saying. Good. So as the gas is moving out, it expels that gas or expel anyhow you call it from the bottom of the rocket. The rocket is moving forward. So the movement of the rocket is dependent on the gases, that hot gas that is leaving from behind it, right? So as it's actually putting out those gas, the rocket is what propelling forward. So the ability of the rockets to move forward is dependent on the gases leaving behind. So that's why we say that action and reaction are equal and opposite. So these are the examples of your action and reaction being equal and opposite, right? And that gives back to you knowing about your free body diagram. Are we together, guys? So the examples I can give you here, number one, I've given about chair. You can write any examples that comes to your mind, or even as you are walking, right? The ground is exerting a force on you as long as you're also exerting a force on the ground, right? So action and reaction, they are equal and opposite. So for examples for JAMB should revolve around these two things. Number one is the recoil of a gun, right? That's a gun and bullet recoil. And bullet recoil. The next one revolves around your rockets. So as to give a context of what I said earlier, I could just put in the brackets, and then I will say that all those hot gases is going to be pushed downwards or backwards, right? And that will now propel our rockets to move forward, right? And your rocket propels pushed forward, right? You can write other examples, but this is the one that is within the context of your exams, right? What next we should look at is in terms of what we call FBD, ability to draw your free body diagram, right? So for your free body diagram, I call it FBD, free body diagram. Now, let's say you have a particular object lying on the floor. What are the forces acting on it? Now, the weight of the object, which you call W, will be acting downwards. So this is your W. Now, that force, which is the reaction force, also known as the normal reaction, right? We call it normal reaction, will be acting upwards in response to that very force. So you have your normal reaction, which represent as R, acting upwards. Now, let's assume that we are trying to pull the object this way. Let's say we are pulling the object. That is a force pulling the object this way. That is your P. In response, the frictional force is going to be dragging it the other way around, preventing it from moving. Remember that FBD simply means free body diagram. Right? So this will be your frictional force, F. Right? So let's assume that this is the direction of motion. If you go through your past questions, you see that sometimes they're going to give you a diagram of a vehicle that is moving. They will tell you that the force moving the body is around 500 Newton, right? And there's a frictional force acting the other way around. Find the resultant force. I've told you before, if the forces are acting in different directions, you add them together, and the direction of the resultant force is going to be towards that side with higher force, right? So it's going to revolve around that. If you are still with me, can you please give me a thumbs up if we are still together? All right, beautiful. And I don't know whether it's in this class that I spoke about the difference between mass and weight, right? Lilia and Uchenna, why are you giving me a thumbs down? What happened? Yeah, can you just tell me what's the problem?
Can you explain again?
Okay, can I explain again? Okay, you didn't say come again. Okay, explain again. So I should explain actually. All right. So you have that. If you had said I should come again, then I will tell you it's going to be on Friday. Now, explain again. You have P, you have F, W, and R. I'm saying that, assuming that this is an object and someone is pulling, let's say that this is Paul. Paul is trying to pull this object to the right hand side. Now, what are the forces acting on this object? The first force acting on this object, W, is the weight of the object. Now, and I told you that the third law said that anytime there's an action, you have something else that will counteract it. So action and reaction are equal and opposite, right? So, and I gave examples. As this body, the weight of this is pressing against this plane, the plane as well is acting upwards. Do you get the point now? I used a table or a chair before. As you're sitting on that chair, you are exerting a force on the chair, and the chair is also exerting a force on you, right? So action, reaction, equal and opposite. So that reaction force is what I represent that R acting upwards. Now, this is frictional force. If I'm dragging this object along this line, it is expected that the frictional force will be resisting the object from moving along that place that I'm dragging it. Does it make sense now? Are you sure? If you don't understand, say, don't have mercy on me, because some students can actually do that. Let me just have mercy on this guy so that the little food he ate this morning will still remain in his stomach. All right, so that's for your free body diagram. And that will take us to, you know that there's a difference between mass and weight. I told you guys the other time that mass is the same anywhere, right? But the weight is going to differ depending on the place where it is, right? I said that the other time. Now, that will lead us, because of this free body diagram, let's quickly look at a concept, right, that is going to really help us in our journey together. Mr. Paul, are you still here? Let's quickly look at weight. All right, welcome, Mr. Paul. Mass, and then normal reaction. Maybe we should fix a time we are going to catch up, so I get to see everybody's face. I will get to meet ourselves as well, right? There should be a time like this. It should be a family time where we'll get to see ourselves and meet each other. You're giving me a thumbs down. Why? Any special reason for that? You don't want us to see you? Talk about inclined plane. Baba. Inclined plane. Inclined plane is like this now. You start having a force here. It goes down. Then you have another one, the normal acting this way. The force here will be equal to the force there. It's very simple. Don't worry. When we get there, we'll cross it. All right. So now, there is something that we call apparent weight, right? Have you seen a question where they say somebody is inside a lift, and this one happens to the lift, and this one happens to the lift? How many persons have seen that question in JAM? If you've written JAM before, right? Have you seen that kind of question? Give me a thumbs up. A man is in a lift, moving upwards, Or a man is in a lift, he's going downwards. Anybody? All right, Mesoma gift, yeah, good. Other persons have not seen that. Yeah, Paul, well done. Good, Susan. All right, so let's quickly look at that. Now, there's something we call your real weight and there's something we call apparent weight, right? So now let's look at that. Real weight and apparent weight. For inclined plane, I'm going to dedicate a class on that to solve as many questions as possible because it can be confusing for students. So I'm going to dedicate a particular class to that. And all we do is also solve questions on inclined plane. Now, let's understand something about your real weight and your apparent weight. When you get a scale, you know that normal scale that they use in checking your weight now when you climb it. Now, when you climb that scale, let's assume that this is the scale and there's a reading on the scale. When you climb this scale, you are exerting a particular force on that scale. That force you are exerting on that scale is W. That scale as well is exerting a force on you, which is R. If you get what I just said, give me a thumbs up. So now, as you climb the scale, it does what? It exerts a force on you. People that work in the hospital, right? Doctors like me will not understand this thing better. You know? So when you climb there, your weight is acting is acting up, is acting downwards, and the scale is exerting its own force on you, right? Good. Now, that said, there is something that we need to understand that happens right there. Because this scale is on the floor, it is not moving. You will see that what is going to record will be equal to your weight, and that W will be equal to R, which means the force you're exerting on the scale will be equal to the force that the scale is exerting on you. Does it make sense? And it records it and gives you your weight. And at that point in time, W becomes equal to R. But you see, when this scale is moving, when there is a movement, let's say you as a person is moving. That's why for those that work in the hospital, while measuring our weight, are we allowed to move our body? Answer, please. If I go to the hospital to check my weight, I climb the scale, are we allowed to move our body? No. Do you know why you're not allowed to move your body? When you move your body, you've altered the measurement. And what will happen is that your W will no longer be equal to your R. There will be a change. Because do you know what that scale is measuring now? What that scale is measuring is not your W. That's your own weight, your real weight. What that object is measuring is what we call your R. That's your reaction force, which is your apparent weight. Which means it is measuring the force. I wish my video is on. If you see the kind of drama I'm acting here, you're going to laugh. It's if you see the way my hand and my legs is moving now, eh? So but it's unfortunate I'm not at my workspace, so it's not convenient to turn on my video at the moment. So now, it's if the what I was saying something in terms of the movement. Now, what that your scale is measuring is your apparent weight, R, which is the force that the scale exerts on you. As you climb, you are exerting a force on it, which is your W. And the scale is exerting a force on you, your R. Now, what that scale is measuring is not actually W, because W is your real weight. What it is measuring is R, your apparent weight. And that is why when you move your body, R is going to change. You get the point now. What am I saying? But at the point you are standing straight, no movement, your W will be equal to your R, so that the apparent weight will give us your actual weight. If you get my point, give me a thumbs up. If you get my point, give me a thumbs up. Yeah, Nikki, good silver. Nikki, good silver. Any day you miss class, I will know. Good. Good. Now, that said, but something happens. This force that this scale, the force that the scale will exert on you can change when there is movement, right? Once there's a change in acceleration, that value is going to change. But you see, your actual weight, your real weight stays the same, but the reading can change based on the change in acceleration. And that is why if you climb a lift, I know you guys must have seen that social media, those is trending. That lift that moves, like the step is moving. Like it's not like the normal lift that when you enter, you just stand there, it takes you up. Like that's one that has something like a moving staircase. Even me, sometimes because of what I've watched in social media, if I go to ShopRite and I see it, I prefer to take the other route. I know some persons are like that as well. I was just prepared to respect myself and take the other staircase up. But that's very bad, actually, right? So, what happens in a lift? Now, if you are in a lift, right? Let's say you went to a hotel to check one or two things, right? Dauda Baraka. My brother, what don't you understand? What's the challenge? Can you talk to me? Have you measured your weight at all? Have you climbed the scale before, Dauda? Feel free to turn on. Okay, now girl, are you serious? Are you a girl or a boy? Sorry, Dauda. Oh wow! I've seen the second name for my daughter. After Ife, it is Dauda. At least I have Yoruba name for my daughter now. I have Hausa name, then Igbo. So I'll have Wazobia in my house. So now, Dauda, what's the challenge, please? Can you type on the chat, or should I? Is the place noisy? Can you turn on your mic and talk, please? Is a very interactive class. About the weight. You know, I might not even know what you mean by the weight. Yeah, turn on your mic and talk. Feel free, okay? Should I go on? Why are you shy? Are you not a people? Okay, weight mass and normal reaction. Okay. Now, now I'm saying that if you have an object, Dauda, right? If you have an object this way, good. I'm saying that, okay, let's say that this is you. This is Dauda. Are you slim or are you chubby? Which one? So now, don't mind me. Okay, all right. You're chubby. That's interesting. So now you have the weight acting downwards this way. This is your weight. So when you sit on that chair, the chair you're sitting currently, your weight is acting downwards. Now that chair is acting on you as you are exerting a force. You know that as you are sitting, you are exerting pressure or force on that chair. That chair as well is exerting force on you. That's why when you that is why when you when you sit on the chair by force, it's going to pain you, right? There's how you're going to sit on the chair, like with so much force, you're going to be receive that very pain. Because as you are sitting with that much force on the chair is also exerting force on you as well, right? So that is why this is your weight. That force is also that chair is exerting a force on you, and that force is exerting on you is acting the other way around, opposite, and that will call the normal force or your normal reaction force. Normal reaction. Do you understand it now? Yeah, Dauda Baraka. Interesting. All right. So now let me now bring it back to the scale I was talking about. Now I was trying to let you know that when you climb your scale, what your scale is measuring is your apparent weight. And Nikki Gold gave me a thumbs up. I think she works in a hospital and she understands this better. Right? So apparent weight, not your real weight, because this real weight, as long as you're on earth, it doesn't change. Like it just remains that way. What is changing is your apparent weight. So now what your scale is measuring is the force it exerts on you. Remember, as you climb the scale, have you seen someone that climbed the scale and the scale stopped working? What it means is that the there's a kind of weight that the scale will see that it cannot accommodate it. So when Dauda, you still there? Give me a thumbs up if you're there, Dauda. Mhm. Dauda, you there? So now you have W here, right? Now, when you stand on the scale, as you're exerting pressure on the or force on the scale is also exerting force on you. So what that scale is measuring is that force it exerts on you. But because when you climb, you are expected not to move your body. Because once there's an acceleration, the force that scale exerts on you is going to change. So when you are standing up without movement, you're going to see that your W will be equal to your R, which means that the real weight is equal to apparent weight, which is what it returns to you. Now, I was talking about you going to the hotel or going to anywhere and you're making use of a lift. When you use a lift, what happens there? You notice something that is as though when that thing start moving, you feel heavier, as if you are heavier. Like if you've used a lift before. Anybody here that have used a lift before? Anybody here that has? If Nikki Gold, do you work in a hotel? Why are you laughing? Now it seems as though, yeah, those people that use lifts, where were you going to? Start talking now. Hmm? All right, so you appear to weigh more. Like immediately the thing starts. Once you press that button, and it takes you up, it's as though that you feel heavy, as if your head is. Titi Lola, I went to hotel. Okay, interesting. So it feels as though your head is like there's this heaviness you start feeling once you start moving up, right? Now, what happens there is that because the lift is good, Dauda, do you work in a hotel? You give me a thumbs up. Now, what happens there is that as the lift is accelerating upward, right? What happens? Remember that you have these forces now. Wow, you do? Interesting. Maybe I'll visit one of these days so you can give me plenty. You guys have a very good place. I can chill and eat a lot of food because the kind of talk I've been talking since this boot camp, a lot of things have gone out of me. So now, in a lift, let's say you are the lift accelerating upward. Please get this concept. Jam doesn't play with these questions. So accelerating upward. If you're accelerating upward, right, it means that the lift pushes you up. Is that also? Lift pushes you up. Pushes you up. Now, in pushing you up, you're going to have that your R, which is the force exerted by the lift on you, is going upward. Right? Now, your weight, W, is acting downwards. Remember that W equal to mg. Are you seeing it now? But because the lift is accelerating upward, let's say that this is you. This is you. Now, this is the lift taking you up. Remember, the lift is going like this, which is your what? R. Now, your weight is acting this way, which is your W, which is equal to mg. Now, the resultant force is going to be what? Since it's going upward, resultant force is going to be what? Since the lift is going upward. Anybody that can tell me now, what would our resultant be? Resultant force on this body now. Someone should talk now. Fast, fast, fast. What will be the resultant force? If the lift is taking me upward, the weight is acting downwards, what should be my resultant force? Fast, fast. Anybody?
W minus R.
W minus R. Remember, it's going upwards.
Yeah, that's R minus W.
Good. R minus W, because it's going to go in the direction of the force. So that means your resultant force is going to be what? R minus W. Right? And that W is what? Mg. Is that also? Remember that your resultant force, F, resultant force, from our Newton's second law, is equal to Ma. Now, for that lift going upward, I'm going to still write everything down again. Just follow me. For that lift going upwards, resultant force is going to be what? R minus W. But our resultant force is equal to what? Ma. So you have that R minus W is what? mg equal what? Equal ma. Right? So that your normal force or the normal resultant, or sorry, the normal reaction force or the reaction force is going to be what? mg or ma plus mg. And at that point in time, you're going to see that this guy is going to weigh more. Like you're going to weigh more. Apparently will be more because r here will be greater than what? Your W. You're going to weigh more. That's why you feel that heaviness because it's going upward. Based on that movement, your apparent weight is going to change, which is the force exerted by the scale or that lift on you. Are we confused? Anybody here that is confused? If you understand what I said, give me a thumbs up, including the calculations. Next one, I'll give Nikki Gold, Lillian, or Lola. All right. The three women of Jerusalem that said they don't understand is Lola, Lillian, and Susan. All right, Susan, look at what I'm saying. Please, I think what you are going to do, call a Dauda so that you can visit their hotel so you can use their lift. Don't once they ask you what are you doing, just tell them you want to use lift. You came for excursion. Now, what I'm saying is that on that lift, now there's something that my bro answered, right? Which is Mr. Paul, right? Paul said something interesting. You have a body. This is the body here, right? This is the lift, and that lift is going upward. Remember that Paul's weight now on this lift is acting downwards. W equal to mg. Now, but the lift is going upward, which means that lift is exerting a force on Paul, and that thing is going to be an upward force, and that upward force is going to be R. Now, resultant force. What is the resultant? Remember that from our calculations in Newton's second law, we'll say that the resultant force, which is this F is net force, not ordinary force. This is F net is equal to ma. From your Newton's second law, resultant force is equal to ma. Now, we said something that we need to get the resultant force. And remember, since this object is moving upwards, what does it tell you? It tells you that R is greater than W. Is that also a thumbs up? R is greater than W based on our idea of resultant force. Good. Nikki, good. Silver. If you're not careful enough, you will fall. At that time, it's moving up because you appear heavier. There's this spin, and also inertial, force of inertial as well, right? Force of inertial as well. You trying to resist the movement also contributes to that. Nikki, good. It seems you've gone to a hotel back to back. That you got to a point where you even fall down. This is interesting. All right. So that said, we have W equal to mg, then your R now. So what I'm saying, remember that when I drew something like this, Titi, Lily, and Susan, remember that when an object is like this, you have R here, you have another object, let's say P. If the objects end up going in this direction, what does that tell us? That P is greater than R. Is that not so? Susan, Lillian, and Titi, give me a thumbs up if you understand what I did now. If this force is pulling this object like this, another one is pulling, and then it moves this way, it means that P is greater. Is that not so? Titi, where are you? Good. Susan, good. Now, what are we trying to say? That if that lift is going upwards, this is my weight. For the fact that it's taking me up, it means that this R, the force exerted by the lift on me is greater because I'm moving in that direction. And my resultant force F net is going to be what? They are acting in opposite direction. So I'm going to have R minus what? W. They're acting in opposite direction. And it's going to move in the direction of R. Then we now have to plug in our values. F net is what? MA equal to R. W is what? Mg. So that my R now will now be equal to what? It's going to be what? MA plus what? Mg. Do you get? Now that's why if you go to your textbook, you now see something like R is equal to M A plus G. So that's the resultant force. That's the apparent weight when I'm on a lift and it's going upward. That's the apparent weight when you're on a lift and it's going upward. Do you understand it now? That's how to calculate the apparent weight on a lift when you are going upwards. And here, you appear to weigh more here because your R is greater than your W when the lift is moving up. Lily, Susan, and Titi. Yes, Titi has grabbed it. Susan has grabbed it. Lillian, don't give me a thumbs up because others are giving me. If you don't understand, feel free. Okay, Dauda, Baraka. Interesting. Dauda, are you Yoruba, Hausa, or Igbo? Which one? Can you type on the chat? I'm looking for Yoruba. Wow. Oh, I was thinking it's Hausa because I needed my daughter to also have an Hausa name, you know. All right. So let's proceed. You can call me Baraka. Oh, wow. I've seen names today. Nikki Good Silva, Baraka. All right. So let's proceed. Now, the second case, we've looked at a case where lift is accelerating upward, right? So let's look at another case where the lift is going downward. Accelerating. Yeah, welcome. We are all great one family, you know. We're one family, and our goal is to pass our jam, have fun, and also pass our exams. You know, that's the goal. You know, that's the goal. All right. So for a lift accelerating upward, right? Now the lift is moving downward. Is that okay? That means Nikki Gold is done. She has gone to the hotel, right, for excursion, and then she's coming back. She has to enter the lift again because she enjoyed it, right? So now the lift is moving downward. Now remember that if the lift is moving downward, she's done. She's coming back. But I know people like Nikki Gold now. Nikki Gold will still be like, ah, nah, this thing is sweet. She will press up again, up, down, up, down. Before you know it, they will lock you up. Now, at this point, you are coming downwards. Now, if you are coming downwards, remember that your weight is acting this way. Is that also? Let's use this for your R. Your R is still acting upward. That's the force of this guy exerted on you, and your weight is still going what? Downwards. This is your weight. W equal mg. Now, what happens when the lift is coming downwards? Now, because it's coming downwards, remember that from our second law, that resultant force F net is equal to MA. Now, who will tell me what the resultant force would be if this guy is coming? I need a girl now. If the resultant force, if the weight is moving downwards now, the lift is moving downward, what will be the resultant force? I need a girl now. I need a girl now. Anybody? Titi, Lillian, Meso, Dauda, Nikki Gold, Susan. Anybody? What other? Let me see the other names. Isi Olua, Ise Olua. Justice, are you in this class? Justice, are you sure you're here? Are you following at all?
Yeah, I'm following.
Are you serious? I've not been hearing your voice at all. Like, hope there's no problem.
No problem.
Okay. Arrow, MA. Don't subtract here. I just need the resultant force here. Only the resultant force. That's what I need. No. Don't sum it yet. Just the resultant force. Good. So that you make heaven. W minus R. Good. Resultant force is what I'm asking. Resultant force. I'm seeing different things here. Justice, can you imagine? Which one is WR? Which one is minus MA? Good. W minus R. Now, I'm asking about the resultant force. That's what I'm asking. Resultant force. I didn't say you should calculate everything for me. Resultant force. Paul, you are here now. You get what we're saying now, right? Good. So the F net now, resultant force. We've done vectors before now. So F net is going to be what? Since the body is moving this way, two forces are acting in opposite direction. But because the movement of the lift is downwards, right? Movement of the force is down, which means W is winning. The weight is winning at this point in time. So resultant force is going to be what? W minus what? R, right? At that point, you have that your F net. Here, what happens is that W is greater than what? R. What happens in this at that point is that your scale is going to weigh less. Like the apparent weight is going to be smaller. And that's why you feel lighter. As you're coming down, you feel lighter. Nikki Gold, is that not so? The feeling when you are going up and the feeling when you are going down. Yeah, I'm using it because even Lillian. Oh, so that's why I'm using both of. I'm using Nikki Gold because I think she has used lift so many times. So as you're coming down, you feel lighter, right? What happens there, Lillian? Okay, you have gone there as well. So that means that it is what lesser, right? The apparent weight, which is what your scale will measure, will be smaller. Remember that what the scale will measure here, what I said here is that R is greater than W. And what happens here is that you feel heavier. Let me write it right here. The scale reading, which is your apparent reading, the scale reading becomes larger. Because what your scale is measuring is the R, which is the force the scale is exerting on you, not your W. Now, for the second part, W equal to mg, here you have that the scale becomes what? The scale reading becomes what? Scalar. Smaller. Sorry. I don't talk tired today. The scale reading becomes smaller. Because what your scale is reading is your resultant, the force is exerts on you, right? So these are resultant force. Result F net, which is your resultant, is W minus R. Now that said, we can now plug in the values. F net is what? MA from your Newton's second law. W is what? Mg minus what? Minus R. Are we there, guys? Good. Now, what can I do here? I can subtract. I can have that MA minus MG is equal to minus R. When you open your past quiz, you're going to see questions like this. Will I lie to you? During my own time, I was textbook. I crammed this thing, bro. I didn't even understand which one is the R or M. I just crammed everything back then. So let's multiply through by negative sign. I'm going to have minus MA plus MG is equal to R. So that R is equal to mg minus ma. So that R equal to mg minus a. So that will be the force when you are moving what? Downwards. That's to calculate your apparent weight, right? When you are moving downwards. So remember, this is your what? Represents your apparent weight. This is your apparent weight when you're moving downwards. Remember, this is your apparent weight as well when you're moving upwards. But remember that when you are not moving, right? When you're just standing on that lift, your R is equal to your W. Is that not so? When the thing is not moving, a thumbs up. Yeah, when it's not moving. So the last, I'm going to do 2 more cases because I'm behind time already. Now let's look at the next one. When you hear about, have you heard about weightlessness before? But why are you laughing, like? What did you remember? Hmm? How is it going? So Baraka, sorry, how is it going? It was a mistake. Okay. Baraka, is it going? Okay, interesting. All right. Justice, are you still there? Justice, are you still there? Um, Susan, Ugu Godlia. Did I pronounce that your name very well? A thumbs up, Ugu, if you are here. Godlina. Yay. Again. All right, so let's proceed. The lift cable that let's see is no. Oh yeah, thumbs up, guys, if you can hear me. All right. All right. All right. Thank you. Thank you. Thank you. Sorry, I don't know what happened. All right. So now, weightlessness, I said something. Let's assume that justice is on the scale, on the lift, and the thing, the cable cuts out, right? That means it's a free fall. Let's say he's coming down, right? And all of a sudden, the thing stops working. Like it becomes a free will, this thing. It just falls down on its own, right? So now that's what we regard as free fall. You know, when your lift is still active and the cables are working properly, it doesn't fall down by force. Like it keeps going gradually because something is controlling it. But all of a sudden, let's say it stops working and then boom, like that just that way. I don't know how to explain what I want to say, but I know you get the point. Like it falls, that's a free fall. Do you get the point? Uh-huh. Other persons, Lillian, Benita, do you understand what I'm trying to say? Right? About that. Yeah, when it snaps and falls, yeah. So now if the lift cable, it's only the guys that are giving me a thumbs up. How about the ladies in the house? Are we still together? Susan, Lillian, Ugu, Titi. Titi, are you still there? Yeah, Baraka, thank you. Who again? Susan, are you there? Yeah, who again am I forgetting? If I forgot your name, you can call yourself. Where is Ferami? She's not on the call. Yeah, she has missed. She's going to watch the recording anyway. So if the lift snaps and then the lift falls freely, right? So what happens there is that remember for your free fall, when we did our free fall, who can tell me when we did free fall, what can you remember from your free fall about acceleration? That formula that changed. What changed in our formula for that motion? Four equations of motion. Under free fall, what changed? Anybody that can remember? For your equations of motion during free fall, something changed. What was that in our formula?
Acceleration.
Beautiful. Acceleration changed. So at that point, A changed to what? To G. Paula, you are doing very well. You're doing very well. See what will happen? One sachet of water for you. Go to the nearest shop in your house, get the water, and pay for it. You are doing very well, bro. All right. A is equal to G, which is acceleration due to gravity. So at that point in time, yes, we know that the object is still there. The lift is still there. You are still here as well, right? But it's a free fall. Remember that resultant, your weight is still acting downwards. Your R is still exerting a force upward. But look at what happens there. A is equal to G. Now, remember that your F net is equal to MA. But who can still tell me at this point, since the object is falling downwards, what is still the resultant force? Even if it is a free fall, what is the resultant force? What's the resultant force?
W minus R.
W minus R. Now, the way your voice is sounding, W minus R. Yeah. So we have the F net. Yeah, thank you, Baraka. Sorry. So that is what? W minus
Just
R. Yeah, Justice. Yeah, I know. Yeah. Someone commented on the chat as well. Justice, I know your voice now. You know, I know your voice. So F net is MA equal to W is MG minus R. So let's simplify. If I do my normal mathematics, right, I'm going to have that MA minus MG is equal to minus R. Multiply through by minus, I'm going to have the R is equal to MG, MG minus, remember your A has changed to what? MA has changed to MG, is that also? Remember that A is equal to G, recall? Good. So I now have MG minus what? MG. Good. So your your reaction force is equal 0. So have you seen that as under this free fall, your apparent this thing is 0. So the scale is going to read 0. So for here, you see that apparent weight equals 0. So what does that mean? So the scale reads 0. This is weightlessness. Does it make sense, guys? I hope these things are making sense. Does it make sense, guys? Justice, thank you. Paul, thank you. How about the ladies in the house? Titi and Co, what's happening? Thank you, Baraka. Meso, sorry, I keep forgetting you. Meso, yeah, Titi. Who again? Lily, yeah, good. Who again? Benita, how's it going? The Olotu, Olotu, are you here? I don't know how to pronounce your name. You've not been so active. How about Ugu? Do you understand what we did now? Ugu, are you there? A thumbs up if you're here. Do you understand it? Then the other lady, Titi, help me pronounce that name. Is it Olotu or something? Help me out, please. She has not been responsive. Even
I think
Suzanne
I
has not
don't
been
know.
responsive.
I think the
I
name
didn't
is
hear you.
Olotu.
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 Mm-mm.
Okay.
Mm-mm.
Okay.
Olotu,
Then
you're wrong.
Olotu.
Yes, exactly.
Oh, yeah, now you started the Yoruba class for me. Ngba. Oh, voilà. Olotu. All right. So we have apparent weight to have weightlessness, and these are the key things. But remember, when the object is not moving, what happens? Our R is equal to W because the apparent weight is going to measure this reading is going to measure my actual weight, right? My the force I'm exerting on it. Does that make sense? Does that make sense? So when you are standing still, your normal, that what the floor puts on you will be equal to what you feel. That's your normal weight. Now, when the lift is going up, right, the floor pushes a lot on you, exert a lot of force on you, and you feel heavier. When the lift is going down, the push is less. It doesn't push so much on you because you feel at that point you feel lighter in terms of your apparent weight. Then for free fall, it means that floor is not exerting any force on you, right? And that's why your scale you feel weightless. Is that okay? So these are key things I want us to always take note of right there. Any question on that? So let's solve examples on this third law that I just highlighted. I spoke about the first law, second law. Let's see questions on that. If you are ready for the questions, give me a thumbs up. Okay. All right, so let's solve questions. Paul, you can as well check from that your platform whether you can get some questions for us as well, so we can get our hands dirty. Yeah. So far so good. I think I omitted something. Real weight. Did I even define your real weight and apparent weight? Right. So let me quickly define that for the moment we'll be reading some of those things. So let me wipe up this. Yeah, I think it's important, right? I should write it down, right? Is that also? I think I should, so that we'll have something to look at when it is time. Mm-hmm. 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 Okay. Paul, have you seen any, or should I come and go ahead with my own questions?
I can go ahead. So I'm still searching for.
Okay. So let's have your real weight. So let me write a few things on it so that you can always remember before we solve problems. And that. Oh boy. Mm-hmm. 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 Okay. Sorry for the delay, guys. I'm just trying to show that. So your real weight is simply W equal mg, right? So this never changes unless gravity changes. And that's why it will change in the moon, because their gravity changes, right? So apparent weight is the force, the ground, Benita, it seems your network is very bad. You keep leaving and joining. Don't worry, once I become the president, everybody will have network. Just vote for me. So this is called normal reaction R. And then I wanted to add something else, and that was the thing I wanted to add is that a weighing scale actually measures R. Are you there? Not mg. Hmm? So apparent weight, which is what your weighing scale measures, is equal to what? R, which is what your scale measures, right? So now these are different cases I handled. Oh wait, I think I should move this off. Paul, have you seen any? I'm waiting for. I'm just trying to arrange our notes so that we ensure that nobody gets confused later on. All right. So where did I stop? I want to ensure nobody gets confused on this. So let's paste here. Good.
So I've sent some to the group.
To the group, right?
Yes, sir.
All right. All right. I'm coming. Let me check it. Meanwhile, I want to correct all of this. And anybody that has that my other line can send that forward that question to that line. Anybody? That question is sent on the group. Have someone done that? Okay, Titi, I've done that. All right, well done. All right, so this is the case one where you are not moving, okay? Just standing on it. So let's write it here so you can always make use of this note. So R is equal to W, R equal to mg, right? And why is it so? You are not moving, no acceleration. So here, no movement. And what happens here? F net is equal to 0. So this is your case 2. Okay, so let's go over to the questions, guys. It's already 12, but I want to touch one or two. Titi, I don't think you sent it to my. Okay, don't worry. Okay. My WhatsApp there is off. Everybody, are you still with us? So get ready. Let's get our hands dirty, guys. Let's get our hands dirty, guys. What's your next class is biology, right? Or chemistry? Which one? The next class is when?
Biology.
Biology. Okay. All right. So for this question now, if I call your name, you answer, okay? But let me import it to the slide. Bro, you got very powerful questions and I love them. But I didn't see anything on the lift. Do you have anyone on lift there? Let me import first. I love the questions. Very interesting. Oh God, power has gone out of me. All right, so let me share my screen. Then remember, I couldn't do momentum and impulse today, right? So in our next class, I'm going to do momentum. I'm going to do impulse. So just get set. It's going to be an interesting class as well. All right, so look at this question. Can you see my screen? Who am I calling for this? Who am I calling for this question? Baraka, what's the answer? Baraka, what's the answer, Baraka, for this very question number? Yeah, so what's the answer? Can you see my screen? What's the answer? Can you see my screen? Confirm you can see my screen, everybody. Everybody, can you see my screen? Good, good. Baraka, you cannot see my screen. Are you sure it's not format? Mesa, what was the answer?
Three.
What?
Newton's third law. Newton's third law.
Okay, Newton's third law. All right, so let's proceed. The next one here. Let me quickly move the slide up. All right, so the next one, the impulse of force is denoted from the Newton's second law as what? Now, let me quickly add something to that my slide on second law. Quickly. Let me add something. Quickly. Where will I add this now? Now look at this place. Let's add something quickly. Look at this. From this equation 3, pay attention. Though I will still elaborate more on this in our next class. Pay attention now, everybody. Pay attention now. If I demarcate this place this way, let me just create a line here. If you cross multiply, pay attention. If you cross multiply these two, right? Cross multiply, here is 1. Let's say I introduce 1 here. If I introduce 1 here, F times 2, are going to have that Ft is equal to mv minus u. This quantity here is what we call impulse. And the one on the right hand side is your momentum. Is that okay? Do you get the point? Give me a thumbs up. So from this second law, the second law still gives birth to impulse and momentum. Right? Second law gives birth to impulse and momentum. So when I forgot to do that, I don't know what I was thinking about. So when you cross multiply, F times 2 will give us Ft, then that will give you this side the momentum already. So impulse equal momentum, even in your second law, from Newton's second law. Right? So that said, you could observe something here from this very question that we have here. Which question was that? I think we've answered this. Good. So now they said the impulse of force is deduced from second law as what? Impulse deduced from second law as what? Who will answer? Send your options on the chart. Let me see. Impulse of a force is deducted Abi, from Newton's second law as what? Answer guys. Answer guys. I'm ending this class by 12:15. Impulse of force is deduced from A. Lillian said A. Another person, Justice said A. Let me go to the chart and see. Paul said A. Justice said A. Ezra said A. Yeah, that Baraka, you can answer. Mesoma said A. All right, good. So now the next one, a ball of mass is kicked against a rigid vertical ball with horizontal. Okay, you can find the impulse on the ball. Don't worry. Now next class, I'm going to handle that very one. Which of these is a contact force? Titi, I want Titilola to answer this one. Which of these is a contact force? Titi, which of these is a, nobody should answer. It is Titilola I want her to answer. Which of these is a contact force? Which of these is a contact force? Titi, if I read it again, I will not do from here. Give me your answer immediately. Oh, she's not on the call. Interesting. Lillian, answer. In fact, everybody sending your answer in the chat very fast. Everybody, your answers in the chat. D, D. Okay, good. D, beautiful, beautiful. Smart guys, smart ladies and gentlemen. Which of the following quantities has the same unit as impulse? Paul, you didn't see anything on elevator. You didn't see any question on elevator. Paul.
I
D,
saw. I
change the
thought I
momentum.
sent.
Okay,
I will
okay,
give.
okay.
I think I
Men and brethren,
sent.
do you know why the? Okay, I will check it. Hope we know why the answer is D. Okay. Are we still? Which one are we answering now? Okay, D, D. All right. Thank you, guys. Makes sense. Now the next one. Okay, this is the question on impulse. This is on bullets, right? Sickness, penetrate the ball if their mass is this, calculate the speed of blood before he hits the wood. Okay, makes sense as well. That will be in our next class. I'm glad I've given the heads up on this. As the doctor from answered this one. Good, my brother. God bless you. So everybody, look up now. I want to solve that question. Hmm? Hmm? I want to solve. This is how the question will look like. They said, number one thing they said here, young people, they said that a body weighing 80 Newton stands in an elevator that is about to move. It is about to move. The force exerted by the floor on the body as the elevator moves upward with an acceleration of 5 meters per second is what? So what are we looking for here? On the chart, what are we looking for?
Force.
If you come force, I will not do from here. What do you mean by force? All of them, are they not force? My God. What do you mean by force? R, good. Awesome resultant. If I catch you, you are not mess up. It is result. You are looking. Have you seen that you've transferred the resultant to my mouth? You are looking for normal force now, the normal reaction force. Look at what they said now. They said a body weighing 80 Newton stands in an elevator is about to move. Yeah, Nikki, good, correct. The force exerted by the floor. Remember, I told you some. I spent so much time explaining this. When you have a body, your weight is you're exerting pressure on the floor. Your weight is exerting pressure on the floor. The floor itself is acting on you as well. Do you understand? And that force exerted on you by the floor is what you call your normal reaction force, R. So what you're looking for here is your R. And beside, they say it's moving upward. Now, when it is moving upward, remember that I can draw my diagram this way. Now, let's say this is you. Now, your force is acting downwards. That floor is acting on you this way. The force is acting on you upward. This is your R. This is your W. But remember something. What's the direction of movement? What's the direction of movement? Guys, what's the direction of the movement of the elevator? What's the direction? Up or down? Upwards. So now this is your direction. It's moving upwards. Direction. Now, what does that imply? It means that my F net is equal to what? Since it's moving upward, that means it's going to be what? R minus W. Is that not so? Now, what else do I know? Good. Now, thank you, Paul. Paul, you're really following, like I said. Now, they've given us our W. They said that W is equal to 80 Newton. They said that M, so they didn't give us M. They gave us that A is equal to what? What's the value of A? A is equal to 5 meters per second. A is 5 meters per second. Now, F net is usually MA. Is that not so? So you have that MA, pay attention, is equal to, you are looking for R, right, minus W. So R will now be equal to what? MA plus your W. Now, the resultant is equal to, I want to show you something very key now. We have that MA, your W, I'm going a very long way just to relate what we've done so far. W is MG, right? So now we have that R is equal to factor out your m. A is what? 5 meter per second. Plus your weight is what? 80. WG is 80 now. Is that also? Do I have people in the house? Good. Which is 80. But remember something. You have that W is equal to mg. W is 80. I don't know the mass, but they gave me G. Sorry. G is what? 10 meter per second now. Acceleration due to gravity. So it means that m is equal to what? 80 over 10. So that m is equal to 8 kg. Right? Hope I'm not doing so much. Are we together, guys? Are we together, guys? Hope I'm not doing too much. Do I need to calculate that mass? The force exerted, acceleration is 5 meter per second. It weighs 80 Newton. So I have W. Hope we're not doing too much. So I have resultant, M is equal to 5. Yes. So this is 8. So 5 plus 8. Wait, I'm making a very brutal mistake here. Yeah, I am. Sorry, guys. I am. So when you factor out M, you now have A plus G. Is that not so? Is that not so? Everybody? Good, good. So now I have that my R is equal to 8 here. G is 5. A is 5, sorry. G is 10. So that R is equal to 8 multiplied by 15. So that the resultant force is equal to 120 Newton. 18 times 15 to give us 120. Everybody, does it make sense? So what I did was to get the value of my M. Everybody, makes sense, right? Everybody, makes sense, right? Okay. I sure do hope it makes sense for everybody. I sure do hope it makes sense for everybody. Right. So for this one, we accepted that here we have over. Let me just put our solution here. We have F over 1 equal to mv minus u all over t. So ft equal to mv minus u. So this side is your impulse. Your impulse. This side, this is your momentum. All right. So everybody all clear, right? So we said that frictional force is our answer for this one. Okay. So we said here is our Newton's third law. Good. So that's how to solve it. All you need to know is which direction is it moving to. Is it moving up or down? Then you apply those formulas I taught you. If it's moving up, you apply that it's moving up. If it's moving down, you apply that it's moving down, right? So Paul, look for more elevated questions and send on the group. Then in our next class, we're going to take it up. We're going to look at momentum. We're going to look at impulse. And as regarding, I'm glad I've introduced recoil of a gun and everything you need to know about recoil of a gun. So in today's class, right, this was my objective, but it's good and fine. We are able to achieve this one. We looked at the meaning of this. We looked at how to draw a free body diagram. We looked at resultant force, right? I looked at inertia and how it affects acceleration. So what is remaining now for us is to do what? Momentum and impulse, Gauss time graph, and conservation of momentum, which is going to be our next class on Friday. Tomorrow is what? Thursday, right? Tomorrow is Wednesday now. Abi?
Thursday.
Can you hear me?
Today is
Yeah.
Wednesday.
Okay, tomorrow is Thursday. Okay. So on Thursday, do you guys have class on Thursday morning? Yeah, on maths on Thursday morning. Do you have class on Thursday afternoon? Check timetable. Do you have class on Thursday afternoon? No. All right. So guys, we're meeting tomorrow afternoon. Let's finish up momentum and impulse. Is that okay? Thursday, let's finish momentum and impulse. Thursday afternoon. Right. Beautiful. So how was the class today? All right. Now, meanwhile, Baraka, can you send me a message on WhatsApp? I don't know if I get to have your. I don't know the name. All right, just send a message on WhatsApp. Let me take notes. Other persons, how was the class today? Justice, go and eat. You don't try. All right, a love emoji from everybody before we dismiss. Love emoji. Thank you, Paul. Thank you, Paul. Nikki Gold Silver. All right. Meanwhile, Nikki Gold Silver, message me. Let me know your names. I don't know. I don't know the name. Maybe your name is different for what you sent for me the other time. Yeah. Nessa, well done. Yeah. Baraka. Yeah. Paul. Lillian, well done. Titi went off the line. I don't know what happened. All right, guys. All the best. Paul, send more questions to them on the group chat. Yeah. Well done, Benita. Benita, how was the session now? All right. Bye, everybody. Let me end the meeting for everyone. Yeah. All right, Mr. Hillary. Yeah. Over to you. So.